Hello and welcome. In this video, we want to begin our journey into understanding one of the core calculus concepts called a limit. But before we can do that, we need to understand two other particular concepts, which are secant lines and average rate of change, because these concepts are sort of part of the machinery and behind the scenes what defines a limit. Okay, so we're going to begin just with some simple examples. So let's take a look at our example 1. So this question has a car that traveled 60 miles forward during a 60-minute time interval, and we're asked, what is its average velocity? So let's remember that velocity is similar to speed. They aren't exactly the same, but they're similar. And the units of velocity are distance over time. And so what it's going to turn out, at least in the terminology we are going to choose to use, is that average velocity is the same as a slightly more general concept in this example called the average rate of change. So let me write that out. So we often abbreviate that AROC, and what that really stands for, whenever you see average rate of change, it really means a change in something. Here it'll be the change in position or distance divided by the change in time. So here our change in position is 60 miles. Our change in time is 60 minutes. And so overall, we get 60 over 60 is 1. We get 1 mile per minute. And that, folks, is the car's average velocity over those 60 minutes. So, just to be clear, it's not saying that the car was going 1 mile per minute the entire time. What it's saying is that on average it was going 1 mile per minute. So sometimes it might have been going faster, sometimes slower. And it turns out that this concept of average rate of change is more general and can be applied to many types of functions, in fact. So I'm going to show you another example that involves an actual function. So here, let me get the example down. Okay, so this example, we again have a car traveling along a straight road, but instead of given, the total distance and total time, we're now just given an equation that describes its position at all moments in time. So remember, kind of what this means is, if you have a road and you have your car, well, whoever, originally came up with the problem has some place that they are thinking of as position 0. And then wherever your car is, the distance from wherever that reference point is your s of t. It's how far the car is from your reference point at time t, and we call that s of t here. And you'll notice that we quite frequently use s for position. Okay, and so now to find average velocity, it's the same formula. So average velocity is going to be the same as the average rate of change, which will be, it'll be the total change in position, or later we'll call this net change. So it's how far the car traveled during that time over the total change in time. Okay. And so the change in position is, well, where did the car end up at the end of the time interval? Well, the time interval is from 0 to 3. So where was the car at time 3? How far from the reference point? It was at position s of 3, whatever that number is, when you plug in 3. And then at time 0, it was at position s of 0, wherever it started. And when I subtract these things, it tells us how far did it go during this time, right? It's where it ended up minus where it begins tells us exactly how far it went. And then the total change in time is just, what's the end time? That was 3 minutes. Beginning time was 0 minutes. Okay, and then you can throw this into your formula. So that would be minus 3 minus 3 squared plus 8. That's all s of 3. And then s of 0 is, let's see, like this. And the bottom is just 3. So if we work all that out, we get 8 minus 9 plus 8 will be minus 1 over 3. So that's 9 over 3, which is 3, and that will again be in the units of miles per minute. Because the top of the fraction had units of miles, the bottom had units of minutes. Okay, and that's exactly our average rate of change. Okay, so that's sort of how you compute it in general. So let me give you the official definition. And so what this definition is saying, it's trying to define the average rate of change of a function over some interval between some number a to some number b. And it's saying it's given by this formula here, which, now it can apply to any function, not just a position or velocity type situation. And it tells you, you take the output at the end of your interval minus the output at the beginning over the difference in the input. And that'll give you always the average rate of change of a function. So that's sort of the formulaic way, or the algebraic way of writing the average rate of change. The other way we need to understand it is graphically. Okay, so let's get a graph going. So we're going to continue the example we had above. Okay, so what we're going to graph here is the function from the previous example that we were doing. So this one here, which gives us the position as a function of time. So on our graph, the horizontal axis will be the t-axis, and this one will be the the position or distance. The vertical one's in miles. Okay, and this function we were looking at up here, if you look at it closely, you'll see that it's a upside down parabola, so the negative. It's been shifted to the right by 3 and up by 8. Okay, so that means 3 is here somewhere, maybe 8's up here somewhere. And then we draw an upside down parabola here. Something like that. And then what we see, if we're trying to compute the average rate of change at least, is that at time 0, the car had some negative position because it's below the x-axis. And then at time 3, because we were looking at the interval from time 0 to 3, it had a position of 8 miles past whatever reference point was being used. So now in this picture, the thing that represents the average rate of change is the line that connects these 2 points. Okay, so let me draw a line there. So this is called a secant line. And if you think about it, the slope of this secant line is exactly the average rate of change, right? Because the vertical distance is s of 3, which is 8, minus s of 0, right? Because it's basically this distance. And then the horizontal axis is this horizontal distance, which is, the larger number minus the smaller number, so that'll be 3 minus 0, which is just 3, right? And so you see that the slope. So what we can say here is, well, first let me give you the proper definition of a secant line. Okay, so the definition says that this term secant line, what that really means is that it's just some line, a straight line, but it has to connect 2 points that lie on the graph of a function, right? So the 2 points we had up in our example up here were this point here and this point here, right? And these were things that were lied on our function in red. So that's an example of a secant line, right? There's many secant lines you could have drawn because there's many different pairs of points you could have chosen. And so the conclusion we can come to is that the average rate of change of a function over an interval from whatever to whatever, as long as b is bigger than a, from a to b, is equal to the slope of the secant line between 2 points, between your starting point, so a comma whatever the output at a is, and b whatever the output at b is. Okay, so the takeaways from this video should be that the average rate of a change of a function is given by this formula. That's an important one. And in the particular case for position and velocity, the average rate of change is equal to the average velocity if you're using the position function. And finally, a secant line is a line connecting 2 points on a graph, and in particular, if you are looking to calculate the average rate of change, that's the same as calculating the slope of the secant line between the points that lie over the inputs of your interval.